Today I'll talk about my work, which is titled Guarding Serverless Applications with Kalium. This is joint work with Liang, Wang from Princeton, Siddhant, Bhagat from Microsoft, and my advisor, Mike Swift. So initially, I'll briefly talk about serverless computing. So serverless computing is an upcoming application deployment model in the cloud. The main difference between a traditional monolithic web application and a serverless application is that in a serverless application, you decompose your application logic into these small stateless functions. And also, the billing model is such that you only pay per invocation of the function. And each invocation of these functions costs around the order of a millionth of a cent. And some of the common players in this field are Google, AWS, Microsoft, and IBM. So before moving on with the talk, I'll briefly explain the example that I'll be using for the rest of this talk. So in this slide, you can see a banking application that has two methods. That is, one is the deposit method, where a user can deposit some money into an account. And the other is the add user method, where the user can add a new user to the bank. So in this case, serverless applications have this notion of a path. So a path is defined as a sequence of functions that is executed in the application. So in this case, if the user or the application logic does the deposit API call, then it would invoke the validate transaction function, which would invoke the read balance function, followed by the compute balance function, followed by the write balance function. And finally, some balance would be updated in an external data store. So in this figure, the purple arrows indicate that a function was invoked by another function. And a function can also send messages to external services during its execution, and they are shown by the green arrows. Finally, the output of the last function in a path can return a value to the application logic. So in this case, the write balance function can return something back to the application logic. Okay, with that out of the way, I'll now talk about some of the issues and security issues in serverless computing. Before moving on, I'll talk about the threat model. So in this work, we assume that the serverless infrastructure is secure. That is, all the infrastructure services like auto-scaling, the function runtime, and such provided by the cloud provider are assumed to be secure. However, we assume that at least one serverless function has a bug which can lead to remote code execution. That is, data that is coming in through the application logic could be untrusted, and that could lead to a compromise of at least one of these serverless functions in the application. Okay, so consider the following attack scenario. Assume that the attacker has compromised the read balance function. Now, the read balance function has the capability to read the balance of any user in the bank. And what the attacker can do is read the balance of a particular user and try and exfiltrate it to an external attacker-controlled server. And the key message here is that confidential information should not flow to unintended external locations. Consider again this scenario where the attacker compromises the validate user function. And what the attacker can do now is to try and submit an invalid transaction to the read balance function. And this would lead this following subpath to be executed. And essentially, what the attacker has done here is that the attacker has bypassed the validate transaction function. And hence, any transaction that is submitted by the user can now be executed unhindered. So finally, at the end of this path, the write balance function would update the balance of a particular user with an invalid value. So the key takeaway here is that data returned to external storage should be the result of a valid path. So we were wondering what we could do to detect these attacks, and we came up with this following insight. So in a traditional web application, all of this logic would be running in a single application, like a monolithic application like a web server or Nginx or something like that. And what the analogous attack here would be that the attacker compromised a function using something like a buffer overflow or some other control flow hijacking attack. And the attacker would then jump to some other point in the program, thereby destroying its semantics. However, with serverless computing, this internal complex control flow is now observable at the network level, because now you can know that you can figure out what is the control flow based on the messages that are passed around in the network. Also, when we looked at prior work like information flow control and web application firewalls, they do not consider the order of the functions in a particular path. So armed with this insight, I'll now describe our system called Kalium. So the main idea behind Kalium is that all executed paths in the serverless application should be valid. In order to do that, we built a system to track the different paths that are executed in the application, as well as to see if it's valid or not. To do that, we build a profile of the application. So that is, we build the expected paths of each function as well as for the whole application. And finally, at runtime, we enforce the paths by augmenting the function runtime to intercept the messages that are generated by each function. Also, a global controller tracks the current path in the whole application. So now that I've talked about paths, I'll talk about what is serverless control flow. So in order to do that, we define two notions, that is the application control flow graph and the function control flow graph. So the application control flow graph depicts the order of function invocations in an application, while the function control flow graph depicts the order of messages sent during the execution of a function. So to be more concrete, this particular path would be part of the application control flow graph, while this part, which depicts the messages sent during execution of the read balance function, those would be part of the function control flow graph. As I said, the application control flow graph depicts the order of messages, order of function invocations in an application. And essentially, the nodes are the functions in the application, and a node and an edge exists between two nodes if a function invokes another function either directly or indirectly through an external service. And also, these edges between functions are labeled with the URLs of the destination function. So for this particular application, this would be the application control flow graph. And this is the part that I talked about earlier. Now, for the function control flow graph, as I said earlier, it's the graph depicting the order of messages sent during the execution of a function. So let's look back at the read balance function. So what I've shown here is the pseudocode of the read balance function. What it would do is read a particular user's balance, and if there is an error, it would send a message to the error logger, else it would carry on with the computation, with the path that is called the compute balance function. However, we only care about the messages that are sent during the execution of the function and not at the end of the function. So only the particular call to the data store would make it to the function control flow graph. So the figure on the right that you see is the function control flow graph. And it's also assumed that each function is assumed to end in exactly one application subpath. So there is no notion of following one path, then returning, and then following another path. So to address the key challenge, that is, the question is, how do we intercept the messages that each function makes? So in order to do that, we used Google's secure container runtime called gvisor. So gvisor essentially runs Linux, emulates Linux in user space. So every system call made by the function can be intercepted and its payload can be inspected. So we focused mainly on network system calls because they are mainly used in sending messages. So in the read balance function, initially it would read the balance of a particular user, and that is allowed by the function control flow graph. And once it reaches the end of the function, gvisor would then contact the global controller to see if the outgoing edge should be allowed or not. And so the global controller maintains the position of the execution. That is the function that is currently executing in its memory. So it can check whether an outgoing edge should be allowed or not. Finally, I'll talk about a qualitative evaluation, as in how Kalium helps us in stopping those two attack scenarios, as well as a small performance evaluation before I conclude. So recall that in the first attack scenario, the read balance function was compromised, and the attacker was trying to exfiltrate some data to an attacker control server. However, in our case, gvisor would intercept this message and then check with the controller to see if this particular transition is part of the application control flow graph. And because it's not part of the application control flow graph, this particular transition is denied. In the second scenario, the attacker had compromised the validate user function and was trying to execute an invalid transaction by directly calling the read balance function. Again, gvisor would intercept this message and query the controller to see if this outgoing transition should be allowed or not, and it's disallowed in the process. So for the performance evaluation, we used the Valve benchmarks. So Valve is an information flow control framework, and it has these benchmarks that also have a comparison with Trapeze, which is also an information flow control framework. And as you can see, Kalium has a relatively low performance overhead as compared to these related works. We also have an evaluation of the graph generation, and there are more details in the paper. That is, we also evaluate how our graph generation techniques have a low false positive rate, and it's relatively easy to get one. So to conclude, we show that enforcing control flow is important for serverless applications. We present Kalium, a control flow integrity framework for serverless applications, which has a reasonably low performance overhead. And we have our artifact that's publicly available, and I'll be happy to take questions. Thank you.